Hello, I'm Will Mandel, and this is my Lab 1 lab report. So, the introduction, the purpose of the lab, we wanted to observe horizontal motion of an object, which I chose to be a marker, at a constant velocity to determine its position over time. And then we made a real life model and then compared it to a GlowScript model that we calculated. And the real life model, it was a marker rolling briefly along a table, so the velocity was constant. Fundamental principles, super fundamental. Newton's first and second laws, and we have our equations here, the position update formula and the velocity update formula we used. We know that Newton's first law is about inertia, and what stays in motion, what is in motion will stay in motion, and no other forces act on it, so we're proving that today. Additionally, Newton's second law explains that it states that the acceleration of an object is directly proportional to the net forces on it and inversely proportional to the mass, which means larger force produces a larger acceleration and a larger mass results in smaller acceleration. We're able to find those based off the two formulas, which aid in our calculations today. In the experiment, we used a marker, a yardstick or a meter stick, and a phone to record the marker's path, which is very important. And we propped up the phone on a table, so we're out of the way of the marker's path. We rolled it down along the meter stick, and we did not touch the marker until it ended on the other side of the frame. This is the experiment. You can see it rolls along our meter stick. And what we have here is our GlowScript. So I found my tracker results, and I made sure my tracker results matched very closely. Hopefully y'all can see that, to my GlowScript. So here's my code. Started with three key things. We have our velocity vector direction, our magnitude of velocity, and our change in time. And we have that in here. And then also, I've written out my Newton's second law and first law equations as instructed here. And we have our graphical comparison. We have our position versus time graph from GlowScript right here. And then we have our real life experiment results, which I overlaid with our GlowScript so you can have a better visual. So this is our calculated and then our experimental position. Very, very similar because it's constant velocity. There's little room for error. And you can see our calculated velocity. It's a straight line since it's constant velocity. Error, there is some error, human error with unwanted spin, changing directions, pushing too hard. And then we also have friction. We didn't really take friction into account at all. Where it immediately slows down, which is why there's a little bit of difference in our velocities. And then there's error within GlowScript, small error margins, and it's pretty much negligible, but everything is worth mentioning because this is very, very important. And what if you flip the axes? And then this experiment, the marker rolled left to right, resulting in motion in negative x direction. And the result of this setup was a negative slope. And when the data was gathered and it was graphed, it was worth noting velocity is constant. But if the axes were flipped and the marker's position would be in the positive x direction of the slope, data would be positive. So the velocity would be unaffected, but the position we've now flipped around. So what does this mean? This is important. It's not possible for our real-life model to have a constant velocity without external forces like friction and the marker experiences when rolling. And even though our table does not have too much friction, the acceleration over time in the negative direction experiences, it slows down. And with GlowScript, there's no feasible friction, so it's not a factor. So this concludes my presentation. Thank you so much for watching. I hope this is applied to all of the rubric points, and I really appreciate you watching. Thank you.